Good evening, ladies and gentlemen. How are you all doing? If I'm not mistaken, you've written a few semester tests last week and you are writing a few this week as well. I'm also doing fine, thank you. So, how are your semester tests going so far? So, good, hectic, so mixed feelings. So, did anyone watch the lunar eclipse this morning? So you at those that watched the eclipse, how was it? I also skipped this one. Lunar eclipses are usually amazing, but lunar eclipses is actually quite a common phenomenon. There's a few actually happening per year. So it's the eclipse this morning. Its maximum was just before 6 o'clock. So let's start with tonight's lecture. So in last week's lecture, we started to discuss the different effects that we have on global warming and how global warming and climate change is all around us. Have you guys literally noticed climate change in your everyday lives? Yes, so what is the effects that you guys have already started seeing? So yes, it's raining in May, so the weather cycle is messed up. Yes, we have flooding. Certain microclimates will change. That means in certain parts of Africa, certain climates will be warmer and certain places will also be a lot colder. You have a palm tree that's blossoming now. Okay, that's interesting. Victoria Weaver, strange no more. Yes, that is all to do with global warming. So let's begin. So, yet another misconception is that the observed warming of Earth is due to natural causes rather than a greenhouse effect. As scientists began to study early indications that Earth's global climate is warming and that humans produced CO2 might be a major cause, they reacted with professional skepticism. They asked questions such as: is global warming really happening? And if the warming is real, is some mechanism other than human activity the main cause? Experiments were conducted, calculations performed, and models created to answer those types of questions. Such research, carried out over decades, revealed that the regular and predictable changes in Earth's axis, inclination, and orientation in the shape of its orbit, called the Milankovitch cycle currently would be driving Earth's climate towards lower, not higher temperatures. Also, observations by space probes indicate that the sun's luminosity, average over its activity cycles, has been constant for decades or has decreased slightly. The observed warming must be strong to be occurring in the face of opposing astronomical effects. So, apologies, what is the scope of our semester test next week? So I will give the scope to you guys tomorrow. So the amount of warming to expect in the future is difficult to predict because Earth's climate is critically sensitive to a number of different factors, not just the abundance of greenhouse gases. For example, a slight warming should increase water vapor in the atmosphere. And although water vapor is another greenhouse gas that would enhance the warming, increased water vapor might cause added cloud cover, increasing Earth's albedo, the fraction of light it receives that is reflected back to space. An increased albedo would then tend to reduce the warming. Also, even small changes in temperature can alter circulation patterns in the atmosphere and in the oceans. And the consequences of such changes are very difficult to model. The situation is complex, but models that best track the warming that has already happened point to substantial continued warming. There's no doubt that civilization is warming Earth through an enhanced greenhouse effect, but the remedy is difficult to imagine. Reducing the amount of CO2 and other greenhouse gases released to the atmosphere is difficult because modern society depends on burning fossil fuels for energy. Political, business, and economic leaders may argue that the issue is uncertain, but all around the world scientists of stature have reached an agreement. Global warming is real, is driven by human activity, and will change Earth. What humanity can or will do about it is uncertain. Human influences on Earth's atmosphere go beyond the greenhouse effect. Our modern industrial civilization is also reducing ozone in Earth's atmosphere. Many people have a common misconception that ozone is bad because they hear it mentioned as a pollutant of city air produced by ozone emissions. Breathing ozone is bad for you, but as you learned earlier in this chapter, the ozone layer in the upper atmosphere protects the lower atmosphere and Earth's surface from harmful solar UV photons. Ozone is an unstable molecule. Certain chemicals called chlorofluorocarbons, CFCs, used for refrigeration, air conditioning, and some industrial processes, can easily destroy ozone. As these CFCs escape into the atmosphere, they become mixed into the ozone layer and convert the ozone back to normal oxygen molecules. Ordinary oxygen does not block ultraviolet radiation, so depleting the ozone layer causes an increase in ultraviolet radiation at Earth's surface. In small doses, ultraviolet radiation can produce a suntan, but in large doses it can cause skin cancers. The ozone layer is especially sensitive to CFCs over the Antarctic and Arctic regions because of their temperatures. Starting in the late 1970s, the ozone concentration fell significantly over the Antarctic, and a hole in the ozone layer developed over the continent each October at a time of the Antarctic spring. Satellite, airborne, and ground-based measurements showed the same thing being to happen at the far north latitudes, with the amount of ultraviolet radiation reaching the ground increasing. Fortunately, as a result of these warnings, international agreements banned most uses of CFCs, and a trend of ozone hole expansion slowed and now appears to have reversed. In image A, we can see satellite observations of ozone concentrations over Antarctica are shown here as red for highest concentration and violet for lowest. Starting in the 1970s, a hole in the ozone layer was observed to develop over the South Pole. The image B, although ozone depletion is most dramatic above the South Pole, ozone concentrations have declined at all latitudes. There is yet another misconception that global warming and ozone depletion are two names for the same thing. Take careful note that the ozone hole is a second Earth environmental issue that is basically separate from global warming. The CO2 and ozone problems in Earth's atmosphere are paralleled on Venus and Mars. When you study Venus in chapter 17, you will discover a runaway greenhouse effect that has made the surface of the planet hard enough to melt lead. Also in chapter 17, you will learn that Mars has an atmosphere without an ozone layer. A few minutes of sunbathing on Mars would kill you. Once again, you can learn more about your own planet by studying exaggerated conditions on other planets. So yes, Mabel, I think you are correct. The last thing I heard, it almost closed up again, or could be closed up right now again, the ozone layer. So yeah, you can go through these slides in your own time, but this is how Earth, a nice summary of Earth and the Moon and how the two compares to one another. So now we're going to start, so let's go back one slide. So now we're going to talk a little bit about the Moon, and I'm assuming with your assignment, you guys can tell me some pretty cool things about the Moon. Definitely moves. What else do you know about the Moon? What interesting facts do you have about the Moon? Or what have you learned about the Moon in your assignment so far? Yes, Mr. Mabel, you're correct. It's slowly drifting away. I think the rate is about 1 or 2 centimeters per year. Yes, the Moon shifts 12 to 13 degrees every night in position. So isn't a problem that it's moving away? So due to the gravitational force of the attraction between the Moon and Earth, yes, it's the decay of gravity, it's moving away. So it's not a problem. It's still going to be here for billions of years, but it's moving away at a rate of between 1 and 2 centimeters per year. And in astronomical terms, that is insignificantly small. So if you had been one of the first 2 people from Earth to step onto the airless surface of the Moon, what would you have said? Neil Armstrong responded to the historic significance of the moment by saying, "That's one small step for man, one giant leap for mankind." Buzz Aldrin was second, and he responded to the Moon itself saying, "Beautiful, beautiful, magnificent desolation." In other words, although it is desolate, the Moon has its own kind of beauty. Many planets in the universe probably look like Earth's moon, and astronauts may someday walk on such worlds and compare them with Earth's moon. Only 12 people have stood on the Moon, but planetary astronomers know it well. The photographs, measurements, and samples brought back to Earth paint a picture of an ancient battered crust and a world created by a planetary catastrophe. The surface of the Moon is divided into 2 dramatically different kinds of terrain. The dark grey areas visible from Earth by naked eye are the smoother lunar lowlands, which, using the Latin word for seas, early astronomers named Maria, plural of mare, which is produced Yeah, it's British Turkey, so it's not May, that's English pronunciation, so Latin pronunciation is Mare. You can also see the comparatively bright, rugged, and heavily cratered lunar islands. The color of moon rocks is dark grey, but Earth's moon looks quite bright in the night sky. In fact, the average albedo of Earth's moon, so the fraction of the light it reflects, is only 0.12. So in other words, the moon reflects only 12% of the light of the sunlight that hits it. In comparison, Earth, thanks mostly to its bright clouds, has an average albedo of 0.31. The moon looks bright only in contrast to the night sky. In reality, it is a dark grey world. Whenever you look on the moon, you find craters. These craters look quite dramatic near the terminator, the name for the boundary between daylight and the darkness on the moon where shadows are long. As you have already learned, the highlands are heavily marked by craters, whereas the smooth lowlands contain relatively few craters. Planetary scientists now know that the craters on the moon were formed by the impact of meteorites. Study and notice 3 important points plus 5 new terms. 1. Impact craters have certain distinguished characteristics, such as their shape and the injector, rays, and secondary craters around them. Secondly, lunar impact craters range from tiny pits formed by micrometeorites to giant multi-triggered basins. And then thirdly, most of the craters on the moon are old. They were formed long ago when the solar system was young. 12 Apollo astronauts visited the lunar lowlands and highlands between 1969 and 1972. Most of the rocks they found were typical of hardened lava, and some were vesicular basalts, which contains holes formed by bubbles in the molten rock. These bubbles are made when lava flows out onto the surface, and the lower pressure allows gas to dissolve in a molten rock to expand and form bubbles. The same thing happens when you open a bottle of carbonated beverage and bubbles form. The presence of vesicular basalts shows that much of the surface of the moon has been covered by successive lava flows. In the dark flat plains of the lunar lowlands, the mare or maria are actually solidified ancient lava. The highlands, in contrast, are composed of rock-containing minerals that have low density and would be among the first to solidify and float to the top of the molten rock. For example, the highlands are rich in anorthosite, a light-colored, low-density rock that contributes to the highlands' bright contrast with the dark lowlands. Apollo 11, the first mission to the moon, landed on the smooth surface of the Mare Tranquillitatis in the lunar lowlands, and the horizon was straight and level. When Apollo 17 landed at Taurus Litto in the lunar islands, the astronauts found the horizon mountainous and the terrain rugged. The large boulder is a piece of ejecta that, at some time in the past, were thrown here from an impact far behind the horizon. Rocks returned from the moon show that the moon once had a deep magma ocean of molten rock. That after the surface solidified, it was heavily fractured by cratering, and that it now affected mainly by micrometeorites grinding away at surface rock. Many of the rocks all over the moon are breccias, a rock made of fragments of broken rock cemented together under pressure. Breccias show how extensively the lunar surface has been pounded by meteorites. Nowhere did astronauts find what would be called bedrock. The entire surface of Earth's moon is fractured by meteorite impacts. Moreover, the astronauts bobbed across the lunar surface under its low gravity. Their boots kicked up the powdery dust. This lunar dust is produced by the continuous bombardment of the lunar surface by tiny meteorites that slowly grind exposed rocks into fine grey grit with a consistency like talcum powder. The LC-ROSS, a Lunar Crater Observation and Sensing Satellite mission, discovered that, at least in one permanently shattered region near the Moon's south pole, there is a significant amount of water ice under the surface dust layer. Over the last 2 centuries, astronomers developed 3 different hypotheses for the origin of the Moon. The fission hypothesis produced that a Moon broke from a rapidly spinning young Earth. The condensation hypothesis suggests Earth and the Moon is condensed from the same cloud of matter in a solar nebula. The capture hypothesis suggests that the Moon formed elsewhere in a solar nebula and was later captured by Earth. Evidence of these ideas had problems and failed to survive comparison with all the evidence. In the 1970s, based substantially on analysis of newly available lunar rock samples, a new hypothesis originated that combined some aspects of the 3 old hypotheses. The large impact hypothesis proposed that a Moon formed when a very large planetesimal, estimated to have been at least as massive as Mars, smashed into the proto-Earth. Such a collision would have ejected debris into space, and model calculations indicate that some of the debris would have settled into a disk in orbit around Earth. The material in the disk would then have quickly collected to form the Moon. So the Moon was made when a Mars-sized planet hit Earth. Is that not right? So yes, that is true. So here we can see an image of it. So the proto-Earth differentiated to form an iron core. Another body, about the size of Mars, that had also formed an iron core, struck the proto-Earth and merged with it, trapping most of the combined iron inside. An iron-poor rock from which the mantles of the 2 bodies formed a ring of debris. Volatiles were lost to space as the particles in the ring began to accrete into larger bodies, and then eventually the Moon formed from the iron-poor and volatile-poor matter in the disk. This hypothesis explains several phenomena. If the collision occurred off-center, it would have spun the Earth-Moon system rapidly and would thus explain the present high angular momentum. If the proto-Earth and the impact had each already differentiated, the ejected material that became the Moon would have been mostly iron-poor mantle and crust, which would explain the Moon's low density and iron-poor composition. Furthermore, the material would have lost its volatile components while it was in space. So the Moon also would have formed lacking volatiles, as was noted in the Apollo rock samples. Such an impact would have melted the proto-Earth, and the material falling together to form the Moon would also have been heated hot enough to melt. This fits the evidence that a highland anorthosite in the Moon's oldest rocks formed by differentiation of large quantities of molten material. The large impact hypothesis survives comparison with the other evidence and is now considered likely to be correct. So it is unsettling to think that once the Earth was also desolate rock, no different from any other rest of the visible universe. Yes, that is true, and that is the point that we're going to discuss in the last chapter of this module. So the 4-stage history of Earth's Moon is dominated by a single fact that makes its unfolding noticeably different from Earth's history and the later stages. The Moon is small, only 1/4 the diameter of Earth. Its escape velocity is low, so the Moon has been unable to hold any atmosphere. It cannot have surface water, and its interior cooled rapidly as its internal heat flowed outward into space. Small worlds have less heat and lose it more rapidly, so the Moon's small size has been critical in determining its history. The Apollo moon rocks, especially an anorthosite from the highlands, show that the Moon must have formed in a molten state. Planetary geologists now referred to the exterior of the newborn moon as magma ocean. So magma is a term for molten rock in general, whereas lava means molten rock flowing on the surface of world. Denser material sank to the bottom of the magma, and as the magma cooled, low-density minerals floated to the top to form a low-density crust. In this way, the moon partially differentiated. So a question, did heat dissipate from the moon in the form of light energy? So no, it would have been dissipated in the form of thermal energy. The radioactive ages of moon rocks brought back by Apollo astronauts showed that the surface solidified about 4.4 billion years ago. The second stage, cratering, began as soon as the crust solidified. And an older island showed that cratering was intense during the heavy bombardment period at the end of planet building. The moon's crust was shattered, and the largest impacts formed giant multi-ringed crater basins, hundreds of kilometers in diameter. The basins that became Mare Imbrium, so Sea of Raisins, for instance, was blasted out by the impact of an object about the size of Rhode Island. This Imbrium event occurred about 4 billion years ago and blanketed 16% of the moon with ejecta. So, question, but the moon is in a vacuum of space, so the heat wouldn't have a medium to transfer. Yes, it will. So you can still lose the space. Remember black body radiation. So even space, it's not a true vacuum, there's just less particles. But space itself has a temperature, black body radiation, as Mr. Melville said. So yes, it will still radiate into space. So I'm sure thermal energy is just a fancy word for light energy. So not really. So some thermal properties, so some objects, for example, a candle flame, radiates energy in heat, so thermal energy, but it will also radiate energy away in terms of light. So depend on what is happening, but it can be both. But in the case of the moon, it is usually thought about as thermal energy. Because we speak about light energy, the moon doesn't create its own light. So the energy we're speaking about is thermal energy. So near the end of the heavy bombardment, a giant impact created a vast crater basin. Faulting in the crust, producing rings of mountains and lava flows, filled the low regions. Today, all but the outlines of the impact have been covered by dark lava flows. By counting craters on different parts of the moon and calibrating those data using radioactive ages of lunar rock samples, planetary scientists have been able to chart the decline of cratering over the first billion years of the solar system's history. By about 3.8 billion years ago, the impact rates had decreased to the current low rate. But before that, there seems to have been a sudden burst of cratering, astronomers called the late heavy bombardment, that might have included the Imbrium event. The primary evidence of this late bombardment comes from observations of the moon. But that sudden storm of impacts must have affected all of the planets in the solar system, including Earth. Those craters on Earth were erased long ago. But they can be seen on other worlds such as Mercury, Mars, and some of the moons in the outer solar system. To understand what astronomers think caused the late heavy bombardment, you'll need to learn more about the formation and evolution of Uranus and Neptune in Chapter 18. Astronomers can calculate the tremendous impacts that formed the lunar basins would have cracked the crust to depths of 10 kilometers or more, and led to the third stage, flooding. Through Earth's moon cooled rapidly after its formation, radioactive decay continued to heat the lunar subsurface material, as it did inside Earth. Parts of the lunar mantle and lower crust remelted, producing lava that followed the cracks up into the giant basins. The basins were flooded by successive lava flows of dark basalts from 3.8 to 3.2 billion years ago, this forming the Mare. So in this image, we can see much of the near side of the moon is marked by large, generally circular lava plains called Mare. The crust on the far side is thicker, and there is much less flooding. Even the huge South Pole Aitken basins contains little lava flooding. In these maps, color marks elevation with the red the highest regions and the purple the lowest. Studies of the moon show that its crust is thinner on the sideward as its side towards Earth, perhaps due to tidal effects. Consequently, while lava flooded the basins on the earthward side, it was unable to rise through the thicker crust to flood the lowlands on the far side. One of the largest known impact basins in the solar system is the Moon's South Pole Aitken Basin. It's about 2,500 kilometers in diameter and as deep as 13 kilometers in places. But flooding has never filled it with smooth lava flows to make an obvious moraine. The fourth stage, slow surface evolution, has been more limited on the moon than on Earth because the moon has cooled rapidly and also lacks water. Flooding on Earth included water, but the moon has never had an atmosphere, and this has never had liquid surface water. With no air and no water, erosion is limited to the constant bombardment of micrometeorites and rare larger impacts. As the moon lost its internal heat, volcanism died down and the moon became geologically dead. So question, are all these conclusions made using simulations via computer or using photographic evidence? I wrote both are used to conclude how the moon was formed. Yes, both are used. So we actually study the moon. So you gather the moon rock itself, you measure the craters, and then you use those data or the analysis that you made on the moon, and you create a mathematical model. And then from the mathematical model, you create a simulation. And then from a simulation, you can determine what is going on. But first, as like we discussed in the opening chapter, we need to get data. So we observe the moon. We gather data from the moon. Then from what we observe, we create a mathematical model. Then from a mathematical model, we create a simulation. Then from simulation, we have an idea of what's going on. Its crust never divided into moving plates, evident from the fact that there are no folded mountain ranges and the moon is now a one-plate object, frozen between stages 3 and 4. So here we can look at practicing science. So if the moon was intensely cratered by the heavy bombardment and then formed great lava plains, why didn't the same thing happen to Earth? So even though the answer to this question seems obvious, scientists still review the logic to test their understanding of basic concepts. In fact, the same thing, heavy bombardment and cratering, did happen on Earth, although the moon has more craters than Earth. The moon and Earth are the same age, and both were battered by meteorites during the heavy bombardment. Some of those impacts on Earth must have been large and giant multi-ringed basins. Lava flows must have welled up through Earth's crust and flooded the lowlands to form great lava plains, much like the lunar moraine. Earth, however, is larger world and has more internal heat, which escapes more slowly than the moon's heat did. The moon is now geologically dead, but Earth is very active, with heat flowing outward from the interior to drive plate tectonics. The moving plates long ago erased all evidence of the cratering and lava flows dating from Earth's youth. Comparative planetology is a powerful conceptual tool in that it allows you to see similar processes occurring under different circumstances. Now employ comparative planetology to explain different phenomena. And then what are we? One of the most fascinating aspects of science is its power to reveal the unseen. That is, it reveals regions you can never visit. You saw this in earlier chapters when you studied the inside of the sun and stars. The surface of neutron stars, the event derived around black holes, the cause of active galaxies, and more. In this chapter, you have seen Earth's core. An engineer is a person who builds things, so you can call a person who imagines things an imaginer. Most creatures on Earth cannot imagine situations that do not exist, but humans have evolved the ability to say, what if? Our ancient ancestors could imagine what would happen if a tiger were hiding in the grass, and we can imagine the inside of the earth. A poet can imagine the earth, the heart of the earth, and a great writer can imagine a journey to the center of the earth. In contrast, scientists use their imagination in a carefully controlled way, guided by evidence and theory. They can imagine the molten core of our planet. As you read this chapter, if you saw the yellow-orange glow and felt the heat of the liquid iron, then you were a scientific imaginer. Human imagination makes science possible and provides one of the great thrills of science, exploring beyond the limits of normal human experience. And that, ladies and gentlemen, is the chapter about the Earth and the Moon. Any questions? No questions? Everyone's still awake? Okay, cool. So, Mr. Marvel, I still need to get back to you on that question. Can you guys guess what is the next part? So the next part we are going to discuss is Mercury, Venus, and Mars. So what can you guys tell me about Mercury, Venus, and Mars? The other terrestrial woods, that's correct. Could Earth have more than one moon? So our Earth and our own moon formed. Earth only have one moon. But yes, there are planets that have more than one moon. So you're correct, there are other terrestrial planets. Mars have dust there, can have dust devils. Yes, they are neighboring planets. Yes. Do you know what this is? Could it have had more than one before we existed? Unfortunately not. So how Earth and the Moon formed is we only have one moon. Mr. Swanepoel, a dust devil in Afrikaans is a warrelwind. So, can you guys recognize this image of what this is? No, so this is a close-up image of Mercury. So yes, Mr. Joshua, you are correct. This is Mercury. So this picture was taken by one of the solar probes that visited Mercury. And what is this? Yes, this is Venus. And this one, yes, this is Mars. In a previous chapter, you compared a geologically active planet, Earth, the largest of terrestrial worlds, with the smallest, Earth's geologically inactive moon. In this chapter, as you continue studying individual terrestrial planets, you can continue comparing the planets with each other, searching for similarities and contrasts. Like people, the terrestrial planets are more alike than they are different. But it is the differences that are most memorable. So a question, I was told to tell you that Brendan from Sitter have some connection issues, but we'll watch recordings later. That is no problem. Thank you for informing me, Mr. Mabel. So as you explore, you will be searching for answers to 4 important questions. Firstly, how is Mercury similar to and different from Earth's moon? Secondly, how does distance from the sun affect a planet and its atmosphere? Thirdly, how does size determine the geologic activity and evolution of a planet? Then lastly, what is the evidence that Venus and Mars were once more Earth-like, and why did they change? Mercury orbits so close to the sun that it is difficult to observe from Earth, and little was known about it until 1974, when the Mariner 10 spacecraft first flew past Mercury and revealed a planet with a heavily cratered surface resembling a larger version of Earth's moon. Analysis of the Mariner 10 space data showed that large areas have been flooded by lava and then cratered. Spectacular new images and data arrived from the Messenger spacecraft that flew by Mercury 3 times before finally settling into an orbit around the planet in 2011. Beginning a close-up investigation, it lasted until it ran out of maneuvering fuel and crashed in 2015. In image A, we can see enhanced color mosaic images from the Messenger spacecraft of the portion of the planet Mercury containing the colorous multi-ringed basin. The color enhancement emphasizes variations in compositions among different parts of the surface. Then in image B, the origin of the spider formation photographed by Messenger is a puzzle. And then C, lobate scrops cross craters indicating that Mercury cooled and shrank, wrinkled its crust after many of the craters had formed. The largest impact feature on Mercury is the Colores Basin, a mountain-ringed basin that Messenger photos reveal as 1,550 kilometers in diameter, resembling the large ringed basin Mare Orientale, so translated the Eastern Sea on Earth's moon. The Colores Basin on Mercury and the Mare Orientale on the Moon both include concentric rings of cliffs formed by large impact. Though Mercury looks moon-like, it does have several features that Earth's moon lacks. Messenger photos revealed a spider of raised ridges appearing to extend from near a medium-sized crater. Geologists are not sure what process could have caused the spider. Images from both Mariner 10 and Messenger reveal long curved ridges called lobate scarps up to 3 kilometers high and 500 kilometers long. The scarps even cut through craters, indicating that they formed after most of the heavy bombardment. The lobate scarps are the kind of faults that form by compression. This suggests that the entire crust of Mercury was compressed long ago. So here you can go through this in your own time, is the comparison between the Moon and Mercury. Mercury is quite dense, and models indicate that it must have a large metallic core. In fact, the metallic core occupies about 75% of the radius of the planet. In a sense, Mercury is a metal planet with a thin rock mantle and crust. Spectroscopic observations indicate that Mercury has an extremely thin atmosphere that may be partly outgassed from the crust and partly captured from the solar wind. The accumulated facts about Mercury don't really help you understand the planet until you have a unifying hypothesis, like a story. It must make sense and bring the known facts together in a logical argument that explains how Mercury got to be the way it is. Mercury is small, and that fact has determined much of its history. Like Earth's moon, Mercury has lost much of its internal heat, and this is no longer geologically active. In the first stage of its planetary history, Mercury differentiated to form a metallic core and a rocky mantle. The presence of a magnetic field about 1% as strong as Earth's is further evidence of a metallic core. You learn in chapter 15 that a condensation sequence could explain a high abundance of metals in Mercury, but detailed calculations show that Mercury contains even more iron than the condensation sequence would predict. Drawing on the large impact hypothesis for the origin on Earth's moon, scientists propose that Mercury suffered a major impact after differentiation that drove away much of the rocky mantle. However, data from MESSENGER, including images of surface hollows in many locations, indicate that a substantial amount of volatiles were incorporated in the crust and subsequently vaporized abundant volatiles would not have survived a ground impact, so an impact may not after all be the explanation for the size of Mercury's metal core. Mercury is now a one-plate planet, much like Earth's moon, and, lacking a significant atmosphere to erode its surface, has changed little since the last lava hardened. A mosaic of MESSENGER enhanced color images of a section of the floor and peak ring mountains of Mercury's Radalada impact basin. The individual frames in this mosaic are about 20 kilometers wide. The rounded depressions called hollows seen in many locations on Mercury may have been formed by sublimation of a volatile component in the surface material. You might expect Venus to be much like Earth. Its diameter is about 90% of Earth's diameter. It has a similar average density and composition, and it is just 30% closer to the Sun. Unfortunately, the surface of Venus is perpetually hidden below thick clouds, and only in the past few decades have planetary scientists discovered that Venus is a deadly hot desert world of volcanoes, lava flows, and impact craters laying within a deep atmosphere of hot gases. No spacesuit is tough enough to allow you to visit the surface of Venus. In a composition, temperature, and density, the atmosphere of Venus is more Hades than heaven. The air is unbreathable, very hot, and almost 100 times denser than Earth's air. So how do planetary scientists know this? Because US and Soviet space probes descended into the atmosphere and in a few cases landed and reported back from the surface. In composition, the atmosphere of Venus is roughly 90% carbon dioxide. The rest is mostly nitrogen with some argon and sulfur dioxide, and small amounts of sulfuric acid, hydrochloric acid, and hydrofluoric acid. There is only a tiny amount of water vapor. On the whole, the composition is deadly unpleasant and would certainly smell bad too. Spectra shows that the impenetrable clouds that hide the surface are made up of droplets of sulfuric acid and microscopic crystals of sulfur. The four main cloud layers in the atmosphere of Venus are more than 10 times higher above the surface than are Earth's clouds. They completely hide the surface. If you could insert thermometers into the atmosphere at different levels, you would find that lower atmosphere is much hotter than that of Earth, as indicated by the red line in the graph. And something interesting, so with the US and Russian landers that has landed on the surface of Venus and sent back pictures, those landers operated a maximum of an hour, then became so hot that the solder literally, these sort of circuit boards, desoldered itself. So the solder actually became liquid again and ran off the PCBs, and that's how those landers were lost. The strange atmosphere is 90 times denser in Earth's atmosphere. So the air you breathe is 1,000 times less dense than water. But Venus, the air is only 10 times less than water. If you could survive the unpleasant conditions, you could strap wings on your arms and fly in Venus' atmosphere. The surface temperature on Venus is hot enough to melt lead. And you can understand that because the thick atmosphere creates a severe greenhouse effect. Sunlight filters down through the clouds and warms the surface, but heat cannot escape easily because the atmosphere is opaque to infrared radiation. Traces of sulfur dioxide and water vapor help trap the infrared, but it is the overwhelming abundance of carbon dioxide that makes the greenhouse effect on Venus much more severe than on Earth. Although the thick clouds on Venus are opaque to visible light, they are transparent to radio waves, so astronomers have been able to map Venus using radar. As early as 1965, Earth-based radio telescopes made low-resolution maps, but later both US and Soviet spacecraft orbited Venus and mapped its surface by radar. Maps made in the early 1990s by the Magellan spacecraft reveal objects as small as 100 meters in diameter. Radar maps of Venus are reproduced using arbitrary colors. In some maps, scientists have chosen to give Venus an overall orange glow because sunlight filtering down through the clouds bathes the landscape in a perpetual sunset glow. Other radar maps have been colored gray, the natural color of the rocks. In yet other maps, lowlands are colored blue, but there are no oceans on Venus. When you look carefully at colored radar maps of Venus, recall that its surface is a deadly dry desert. By international agreement, names on Venus are all female, with 3 exceptions. Maxwell, a high mountain, and Alpha Reggio and Beta Reggio, 2 high volcanic peaks, which were all named before the IAU naming convention for Venus was adopted. So the IAU is the International Astronomical Union. Radar maps show that Venus is similar to Earth in one way, but strangely different in other ways. Nearly 75% of Earth's surface is covered by low-lying basalt seafloors, and 85% of Venus' surface is covered by basalt lowlands. There is no liquid water on Venus. However, so its lowlands are not really seafloors, and the remaining highlands are not like well-defined continents you see on Earth. Whereas Earth is dominated by plate tectonics, something different is happening on Venus. The highland area, Ishtar Terra, named for the Babylonian goddess of love, is about the size of Australia. At its eastern edge, the mountain called Maxwell Montes rises to an altitude of 12 kilometers, with the impact crater Cleopatra on its lower slopes. For comparison, Mount Everest, the tallest mountain on Earth, is 8.8 kilometers high. Bounded by mountain ranges in the north and west, the center of Ishtar Terra is occupied by Lakshmi Plum, a great plateau about 4 kilometers above the surrounding plains. The collapse calderas Colette and Sacajawea suggest that the Lakshmi Planum is a lava plain. The mountains bounding Ishtar Terra, including Maxwell, resemble folded mountain ranges, which suggests that limited horizontal motion in the crust as well as volcanism may have helped form the highlands. 3 radar maps showing different aspects of Venus' surface is shown in this figure. The main map at top shows elevation for most of the planet. omitting the polar areas. The inset map at the left shows the electrical property of surface minerals related to chemical composition, and a detailed map of Maxwell-Maltz and Lakshmi Planus inset at right is colored to show degree of terrain roughness, with the purple representing smooth and orange rough. As usual, you learn more about other worlds by comparing them with each other and with Earth. So notice 3 important ideas plus 2 new terms. First, there are 2 main types of volcanoes found on Earth. Composite volcanoes are associated mostly with plate boundaries, and shield volcanoes are associated with hotspots that are not related to plate boundaries. Volcanoes on Venus and Mars, unlike on Earth, all have the shape of shield volcanoes, the kind produced by hotspot volcanism rather than by plate tectonics. And then thirdly, some volcanoes on Venus and Mars are very large. They have grown to great sizes because of repeated eruptions at the same place in the crust. This is also evidence that neither Venus or Mars has been dominated by horizontal plate tectonics like Earth's. Many features on Venus testify to its volcanic history. Radar maps reveal shield volcanoes and long lava channels. Other volcanic features include the coronae circular bulges up to 2,600 kilometers in diameter, bordered by fractious volcanoes and lava flows. Coronae appear to be produced by rising convection currents of molten magma that push up under the crust. When the magma withdraws, the crust sinks back, but the circular fractures mark the edge of the corona. Volcanic features on Venus. In A, arrows point to a 600 kilometer segment of Baltus Valles, the largest lava flow channel in the solar system. It is at least 6,800 kilometers long. Then image B, Ain Corona, about 200 kilometers in diameter, is marked by faults, lava flows, small volcanic domes, and pancake domes of solidified lava. Then in image C, this perspective view shows a hill typical of those associated with corona. Molten lava below the surface appears to have pushed up the hill, causing a network of radial faults. No astronaut has ever stood on Venus, but a few spacecraft have landed on the surface and survived the heat and pressure for a few hours. Some of those spacecraft analyzed nearby rocks and snapped a few photographs. The surface rocks on Venus are dark grey basalts, much like those in Earth's ocean floors. This is further evidence that volcanism is important on Venus. While you are thinking about volcanoes, you can correct a common misconception. The molten rock that emerges from volcanoes comes from pockets of melted rock in the upper mantle and lower crust, and not from a planet's molten core. In this image, we can see the Venera 13 lander touched down on Venus in 1982 and carried a camera that swiveled from side to side to photograph the surface. The orange glow is produced by the thick atmosphere. When that is corrected to produce the view as it would be under the white light, you can see that the rocks are dark grey. Isotropic analysis suggests they are basalts. So here we can see the horizon of Venus is visible at the top corners of this image, so over here and over here. And here we can see the instrument cover ejected after landing and the edge of the spacecraft. Radar images show that Venus is also marked by numerous craters. The atmosphere protects the surface from stellar meteorites that would produce craters smaller than 3 kilometers in diameter. Larger meteorites penetrate the atmosphere and have formed about 10% as many craters on Venus as on the morae of Earth's moon. The number of craters show that the crust is not as ancient as the lunar morae, but also not as young as Earth's active surface. The average age of the surface of Venus is estimated from crater counts to be roughly 500 million years. Geologic processes are not renewing the surface of Venus as rapidly as Earth's surface. but no heavily cratered terrain or large impact basins remain on Venus from the heavy bombardment era. So, Mr. Neville, you're saying, didn't they accidentally take the compression of the lens cap instead of the ground, or was that another planet? I'm not sure, but it could be Venus. Impact crater Howe in the foreground of this Magellan radar image is 37 kilometers in diameter. Craters in the background are 47 kilometers and 63 kilometers in diameter. Those radar maps have been digitally modified to represent the view as from a spacecraft flying over the craters. To tell the story of Venus, you must draw together all the evidence and find hypotheses to explain two things: the thick carbon dioxide atmosphere and the peculiar geology. Calculations show that Venus and Earth should have outgassed about the same amount of carbon dioxide, but Earth's oceans have dissolved most of Earth's carbon dioxide and converted it to sediments such as limestone. If all of Earth's carbon were dug up and converted back to carbon dioxide, our atmosphere would be as hot, as dense as the air on Venus, and composed mostly of carbon dioxide, like Venus's atmosphere. This suggests that the main difference between Earth and Venus is the lack of water on Venus that would have removed carbon dioxide from the atmosphere. There is evidence that Venus had oceans when it was young, but being close to the sun, it was warmer, and the carbon dioxide in the atmosphere created the greenhouse effect that made the planet even warmer. That process could have vaporized any oceans that did exist and reduced the ability of the planet to purge its atmosphere of carbon dioxide. As more carbon dioxide was outgassed, the greenhouse effect grew and even more severe. Thus, Venus was trapped in what is called a runaway greenhouse effect. The intense heat at the surface may have affected the geology of Venus by making the crust more flexible, so that it was unable to break into moving plates as on Earth. There are no signs of real global plate tectonics on Venus, but rather evidence that convected currents below the crust are deforming the crust to create coronae and pushed up mountains such as Maxwell. Other mountains, like those around Ishtar Terra, appear to be folded mountains caused by limited horizontal mountains in the crust, driven perhaps by convection in the mantle. The small number of craters on the surface of Venus indicates that the entire crust have been replaced within the last half-billion years or so. The resurfacing may have occurred in a planet-wide overturning as the cold crust broke up and sank, and lava flows created a new crust. Hypothesizing such drama may not be necessary, however. Models of the climate of Venus showed that an outburst of volcanism could increase the greenhouse effect and drive the surface temperature up by as much as 100 degrees Celsius. This could further soften the crust, increase the volcanism, and push the planet into a resurfacing episode. This type of catastrophe may happen periodically on Venus, or the planet may have had a single geologically recent resurfacing event. In either case, unearthly Venus may eventually reveal more about how our own world works. Now we're going to start discussing Mars. So Mars is a medium-sized world, about half the diameter of Earth. The surface is old, cratered, and marked by volcanoes, but as we explore, watch for evidence that water once flowed there. The Martian air contains 95% carbon dioxide, 3% nitrogen, and 2% argon. That is much like the chemical composition of the air on Venus, but the Martian atmosphere is very thin. less than 1% as dense as Earth's atmosphere, 1/10,000th as dense as Venus' atmosphere. There is very little water in a Martian atmosphere, and the polar caps are composed of frozen water ice coated over by frozen carbon dioxide, so dry ice. As summer comes to a Martian hemisphere, planetary scientists observe that the carbon dioxide in that polar cap turning from solid to vapor and adding carbon dioxide to the atmosphere, while winter in the opposite hemisphere is freezing carbon dioxide out of the atmosphere and adding that to that polar cap. Liquid water cannot survive on the surface of Mars because the air pressure is too low. Any liquid water would immediately boil away. And if you stepped out of a spaceship on Mars without your spacesuit, your body heat would make your blood boil. Whatever water is present on Mars must be frozen in the polar caps or in the form of permafrost within the soil. Although the present atmosphere of Mars is very thin, you will see evidence that a climate once permitted liquid water to flow over the surface. So Mars must have once had a thicker atmosphere. As a terrestrial planet, it should have outgassed significant amounts of carbon dioxide, hydrogen, and water. Because it was small, it could not hold on to its gases. The escape velocity of Mars is only 5 kilometers per second, less than half of Earth's, so it was easier for rapidly moving gas molecules to escape into space. Another factor is the temperature of the planet. If Mars had been colder, the gas molecules in its atmosphere would have been traveling more slowly and would not have escaped as easily. You can see this in figure 17.8, that plots the escape velocity for each planet versus the temperature of the region from which molecules would escape. For Earth, the temperature is that of the upper atmosphere. For Mercury, the temperature is that of the hard rocky surface. Clearly, small worlds cannot keep atmospheric gases easily. So here we can see this. So this plot describes the ability of different planets to retain atmospheric gases. Each red dot represents a temperature and escape velocity from the labeled planet. The blue curves indicate how typical highest velocities of gas atoms and molecules, are labeled on the right ends of the curves, depend on temperature and particle mass. Gases that a given planet can retain correspond with curves falling below the planet's data point. And Jovian planets, left and upper left portions of that plot, have high escape velocities and can hold on to low mass molecules. Mars, bottom center, has relatively weak gravity, and although it has a low temperature, can hold only more massive molecules. The Moon has such a low escape velocity that all gas particles can escape. It does not have a permanent atmosphere. So in your own time, you can go through this diagram of Venus compared to Mars. The further problem is that Mars has no ozone layer to protect its atmosphere from ultraviolet radiation, so sunbathing on Mars would be a fatal mistake. The ultraviolet photons can break atmospheric molecules up into smaller fragments, which escape more easily. For example, water can be broken up into hydrogen and oxygen. This Mars is large enough to have had a substantial atmosphere when it was young, may have had water falling as rain and collecting in rivers and lakes. It gradually lost much of its atmosphere and is now a cold, dry world. If you ever visit another world, Mars may be your best choice. You will need a heated, pressurized spacesuit, but Mars is much more hospitable than the Moon or Venus. It is also more interesting, with weather, complex geology, and signs that water once flowed over its surface. You might even hope to find traces of ancient life hidden in the rocks. Spacecraft have been visiting Mars for almost 40 years. 2 Viking landers first touched down in 1976. Rovers Spirit and Opportunity landed in 2004, carrying instruments to explore the rocky surface. The Phoenix Robot Laboratory landed in the North Polar region in March 2008. The sophisticated rover laboratory Curiosity landed and began its exploration of Mars in 2012. And we had, what was the latest one that landed on Mars? Why can't I remember the name? Yes, Curiosity. But remember, Curiosity landed in 2012. So which is the latest one? Let me just quickly look. Yes, I saw that dwarf found on Mars, but that could be edited photos. So the latest one that was landed was Perseverance in 2021. So the dwarf found on Mars, so we are really skeptical about it. So it's usually when something like that happens, it's usually internet hoax. If it was true, there would have been press releases, a press conference, like that you watched the press conference last week about the Sagittarius A star, the black hole in the middle of our own galaxy. So if there was really a door discovered, there would have been a similar press release. So in image A, rovers Spirit and Opportunity were directed from Earth to move across the surface of Mars, explore features, dig in soil, grind the surface of rocks to explore the interiors, and make spectroscopic analysis. Image B, rover Spirit's discovery of sulfate deposits in the soil confirms other evidence that a body of salty water once covered the area and evaporated, leaving the sulfates behind. Images made by a series of orbiting probes showed that the southern hemisphere of Mars is a heavily cratered highland region, estimated to be at least 2 to 3 billion years old. The northern hemisphere is mostly a much younger lowland plain with fewer craters. This lowland plain may have been smoothed by lava flows, but growing evidence suggests that it was once filled with an ocean, a controversial hypothesis discussed in the next section. Then volcanism on Mars is dramatically evident in the Tharys region, a highland region of volcanoes and lava flows bulging 10 kilometers above the surrounding surface. A similar uplifted volcanic plain, the Elysium region, is more heavily cratered and eroded and appears to be older than Tharys bulge. The lack of many impact craters suggests that some volcanoes have been active within the last few 100 million years. These hemisphere maps of Mars are color-coded to show elevation. The northern lowlands lie about 4 kilometers below the southern highlands. Volcanoes are very high, and the giant impact basins, the Hellas in Argyre, are low. So note that the depths of the canyon Valles Marineris, the two Viking spacecraft landed on Mars in 1976, Pathfinder in 1997, and Rover Spirit plus Opportunity in 2004. The Phoenix landed in 2008, Curiosity in 2012, and Perseverance in 2021. High volcanoes and deep canyons mark the surface of Mars. 3 large shield volcanoes in the Pharos region, plus Olympus Mons, stand out in this false color image. Olympus Mons is much larger than Mauna Loa, the largest mountain on Earth. The vast size of Olympus Mons is evidence that the crust of Mars must have remained stationary over the hot spot. So the magma source on Mars has not had horizontal plate tectonics. The Valles Marineris Canyon complex extends across a distance equal to the width of the continental United States. The 3 Tharys volcanoes are also visible in the Viking spacecraft photo. The fact that Valles Marineris borders the Pharos Rise is evidence of some planetary scientists that they have a common origin. All of the volcanoes on Mars are shield volcanoes, which you learned earlier are produced by hot spots penetrating upward through the crust and are not related to the plate tectonics. Olympus Mons, the largest volcano on Mars, is 600 kilometers in diameter, and its base rise is 22 kilometers high. So the largest volcano on Earth, Mauna Loa in Hawaii, rises 10 kilometers above its base on a sea floor. Mauna Loa is so heavy that it has sunk into Earth's crust, producing an undersea moat around its base. In contrast, Olympus Mons, more than twice as high, has no moat and is surrounded entirely by Martian crust. So evidently the crust of Mars is stronger and thicker than Earth's. So if you think Olympus Mons is 22 kilometers high, Mount Everest is roughly 8 kilometers high. The size of Olympus Mons also provides clear evidence that plate tectonics has not been significant on Mars. On Earth, shield volcanoes such as those that form the Hawaiian Islands occur over rising currents of hot material in the mantle. Because the plate moves, the hot material heats the crust in a string of locations and form a chain of volcanoes instead of a single large feature. The Hawaiian Islands are merely the most recent of a series of volcanic islands called the Hawaiian Emperor Island Chain, which stretches nearly 5,800 kilometers across the Pacific Ocean floor. In contrast, a lack of plate motion on Mars has allowed rising currents of magma to heat the crust repeatedly at the location of Olympus Mons, and other volcanoes building huge volcanic cones much larger than any on Earth. When the crust of a planet is strained, it may break, producing faults and rift valleys. Near the Pharos region is a great valley, Valles Marineris, named after Mariner 9 spacecraft that first photographed it. This valley has a block of crust that has dropped downward along parallel faults. Erosion and landslides have further modified the valley into a great canyon stretching almost 1/5 of the way around a planet. It is 4 times deeper, nearly 10 times wider, and over 10 times longer than the Grand Canyon. The number of craters in the valley indicates that it is 1 to 2 billion years old, placing its origin sometime before the end of most active volcanism in the Pharos region. Before you can tell the story of Mars, you must consider a difficult issue: water. How much water has Mars had? How much has been lost? And how much remains? The quest for water on Mars is exciting because biologists are sure that life on Earth depends on water. You will learn in this section that Mars evidently had abundant liquid water on its surface for at least as long as it took life to arise on Earth. If conditions under which life started on Earth existed on Mars at the same time, then Mars provides a real opportunity for scientists to check the hypothesis about how life began on Earth. Beginning in 1976 with the Viking program and continuing to the present day, spacecraft orbiting Mars, such as Mars Odyssey, which reached Mars 2001, Mars Express in 2003, and the Mars Reconnaissance Orbiter in 2006, have returned photos showing that water once flowed over the surface. All of those missions, except Viking, are still operating at the time of this writing of July 2016. As you have learned, liquid water cannot exist now on the Martian surface because it would boil away in the extremely low atmospheric pressure. So evidence that water once flowed on Mars means that the surface conditions there must have been quite different long ago. So I'm glad your chemistry tests went quite okay. Several types of formations hint at Martian surface water. Outflow channels appear to have been cut by massive floods carrying as much as 10,000 times the volume of water flowing down the Mississippi River. Such floods apparently swept away landscape features and eroded deep channels. The number of craters formed on top of the outflow channel showed that they are billions of years old. Valley networks look like meandering riverbeds that probably formed over long periods. The valley networks are also located in a heavy cratered southern hemisphere, so they must be very old as well. There are many other signs that there has been water on the Martian surface, some of which are geologically recent. Regions of collapsed terrain appear to be places where subsurface water has drained away. Gullies leading downhill appear to have been eroded recently, judging from the lack of craters, and a few gullies have been seen to appear between one Martian year and the next. In 2015, the Mars Reconnaissance Orbiter made spectroscopic observations confirming present-day seasonal underground water flows. These images made by the Viking orbiters show some of the features that suggest liquid water on Mars. In image A, outflow channels are broad and shallow and deflect around obstructions such as craters. They appear to have been produced by sudden floods. And then in image B, valley network resemble drainage patterns and suggest water flowing over long periods. Crater counts show that both formations are old, but valley networks are older than outflow channels. Some regions appear to have collapsed because of the withdrawal of subsurface water. Splash craters suggest that water was present in the crust. A runoff channel resembles a meandering riverbed. Gullies appearing in steep slopes during a single Martian year may indicate water flowing from melted permafrost, and a central channel suggests long-term flowing water. Many flow features lead into northern lowlands, and the smooth terrain there has been interpreted as an ancient ocean floor. Features along the edges of the lowlands are comparable to the shorelines, and many planetary scientists conclude that the northern lowlands contained an ocean when Mars was younger. Did Mars once have enough water to fill a sea? Deuterium is 3 to 5 times more abundant relative to normal hydrogen in the Martian atmosphere than on Earth, suggesting that Mars once had at least 20 times more water vapor than that now. Presumably, much of that water was broken up by solar UV radiation, and a normal hydrogen disproportionately lost to space, like the process hypothesized to have destroyed Venus's water. So, question: if life is heavily dependent on water, then why isn't there some kind of life on the Jovian planets such as Uranus and Neptune? I mean, some kind of resilient bacteria at least. And then what was you, Mr. Nabel? I think this was mentioned a while ago, but for the moon assignment, the plagiarism check is due today. Does that mean we can no longer access it after today, or will it remain open until the end of the month? So the plagiarism check will remain open until the due date for the assignment will remain open. And then so as far as I know, the exam will also be online. So we'll have an online test and online exam, unless something has changed. But as far as I know, everything is still online. And then, yes, going back to your life. So the last chapter of this module, we will have an entire lecture just on the possibility of other life. And yes, that is possibilities being investigated. So one of the area of interest is the moon Europa that might support life. So will we have to download a specific browser? No, you can use any browser that you seem fit. Abundant Mars water could survive frozen in the soil and crustal rocks. Instruments aboard the Mars Odyssey spacecraft detected water frozen in the soil over large areas of the planet. If you added a polar bear, changed the colors, and hit the craters in figure 17.14, it would look like the broken pack ice on Earth's Arctic Ocean. Mars Express photographed these dust-covered formations near the Martian equator, and the shallow depth of the crater suggests that the ice is still there, just below the surface. In image A, like the broken pack ice, these formations near the equator of Mars suggest floating ice that broke up and drifted apart. Scientists proposed that the ice was covered by a protective layer of dust and volcanic ash and may still be present. In image B, radar aboard the Mars Express satellite probed beneath the surface to image water ice below the South Polar Cap. The black circle is the area that could not be studied from the satellite's orbit. Then image C. This view from a Phoenix lander shows the landscape of Mars' North Polar Plain, including polygonal cracks understood to result from seasonal expansion and contraction of ice under the surface. Then in image D, in some regions of the North Polar Cap, layers of ice plus dust with different orientations are superimposed, suggesting periodic changes in the Martian's climate. Much more of the ice on Mars may be hidden below the polar caps. Radar aboard the Mars Express orbiter was able to penetrate 3.7 kilometers under the surface and map ice deposits in the crust of the planet's south polar region. There is enough water there, at least 90% clear, to cover the entire planet to a depth of 11 meters. The Phoenix probe landed in 2008 near Mars' North Pole, finding water ice mixed with the soil, not only as permafrost but also as small chunks of bare ice, indicating there once was standing water that froze in place. Rover Spirit and Opportunity landed in areas suspected of once having had water on their surfaces. As of July 2016, Opportunity was still roving and communicating with Earth near 12 years after they had landed. So far as I know, Opportunity stopped working around about 2019-2020. Both rovers have found evidence of past water, including small spherical concentrations of the mineral hematite, dubbed blueberries, that require abundant water to form. In other rocks, Opportunity found layers of sediments with ripple marks and cross layers showing they were deposited in moving water. Chemical analysis of the rocks at both Opportunity and Spirit sites detected sulfates, much like Epsom salts, plus bromsides and chlorides. On Earth, these compounds are left behind when bodies of water such as desert lakes dry up. In its first year at work, Curiosity rover discovered rounded rocks of the sort produced by running streams. In image A, rover Opportunity photographed hematite concentrations, so blueberries, weathered from rock. The round mark is a spot cleaned by the rover. The spheres appear to have grown as minerals collected around small crystals in the presence of water. Similar concentrations are found on Earth. Then in image B. The layers of this rock were deposited as sand and silt in rapidly flowing water from the way the layers curve and cross each other. Geologists can estimate that the water was at least 10 centimeters deep. A few blueberries are also visible in this image. Mars has water, but it is hidden. When humans reach Mars, they will not need to dig far to find water in the form of ice. They can use solar power to break the water into hydrogen and oxygen. Hydrogen is fuel and oxygen is the breath of life. So the water on Mars may prove to be buried treasure. Even more exciting is the knowledge that Mars definitely once had bodies of liquid water on its surface. It is a desert world now, but someday an astronaut might scramble down an ancient Martian streambed, turn over a rock and find a fossil. It is even possible that life started on Mars and has managed to persist as the planet gradually became less hospitable. For example, life may have hung on by retreating to limited warm and wet oases underground. You will learn in the final chapter about possible evidence of ancient life in one of the Martian meteorites. Did Mars ever have plate tectonics? Where did the water go? These fundamental questions challenge you to assemble the evidence and hypothesis for Mars and tell the story of its evolution. The four-stage history of Mars is a case of arrested development. The planet began by differentiating into a crust, mantle, and core. Studies of its rotation reveal that it has a dense core. The Mars Global Surveyor spacecraft detected no planet-wide magnetic field, but it did find regions of the crust with fields a bit over 1% as strong as Earth's. Apparently, the young Mars had a molten iron core and generated a magnetic field, which became frozen into parts of the crust. The core must have cooled quickly and shut off the dynamo effect that was producing the planet-wide field. The magnetic regions of the crust remained behind like fossils. The crust of Mars is now quite thick, as shown by the mass of Olympus Mons, but it was probably thinner in the past. Cratering may have broken or at least weakened the crust, triggering lava flows that flooded some basins. Most of the northern hemisphere may have been a huge impact basin that was later filled with water, cratering a Martian ocean that has since vanished. Mantle convection may have pushed up the Ferrous and Elysian volcanic regions and broken the crust to form Valles Marianus, but moving crustal plates never dominated Mars. There are no folded mountain ranges on Mars and no sign of plate boundaries. The large size of volcanoes on the planet is evidence that the crust does not move. Planetary scientists therefore conclude that as Mars' interior cooled, its crust grew thick and immobile. At some point in the history of Mars, water was abundant enough to flow over the surface in great floods and may have filled oceans. But the age of liquid water must have ended more than 3 billion years ago. The climate of Mars has changed as atmospheric gases and water were lost to space and as water was frozen into the soil as permafrost. For Mars, the fourth stage of planetary development has been one of moderate activity and slow decline. Volcanoes may still occasionally erupt, but this medium-sized planet has lost much of its internal heat, and most volcanism occurred long ago. The atmosphere is thin, and the surface is a forbiddingly dry, cold desert. Venus and Mars share at least one characteristic. They have evolved since they formed and are now quite different than they were when the solar system was young. Moreover, as you have learned, planetary scientists have evidence that the surface conditions on Venus, Earth, and Mars were much more similar long ago than they are now. So notice 4 important points. So firstly, the difference between Venus and Earth is not the amount of CO2 they have outgassed, but the amount they have removed from the atmospheres. Being warmer, consequently having less liquid water on its surface, sealed Venus' fate as a runaway greenhouse. Venus is highly volcanic, with a crust made up of lava flows that have covered over any older crust. The entire planet have been resurfaced with the last half billion years. Thirdly, Mars is significantly smaller than Earth, with gravity too weak to prevent much of its atmosphere from leaking away. Evidence shows that Mars once had liquid water on its surface, but much of its water has been lost to space. The low atmospheric pressure means that the only remaining water is frozen in the soil. And lastly, because Mars is small, its interior cooled relatively quickly, and volcanism has died down. The lack of volcanism means the escaping atmosphere is not replenished. The planet's crust was thinner when a planet was young, but has grown thick and never broke into moving plates as did Earth's crust. And then Mars has moons. So unlike Mercury or Venus, Mars has moons. The small and irregular in shape Phobos is 28 by 23 by 20 kilometers, and Deimos 16 by 12 by 10 kilometers are probably captured asteroids. Photographs reveal a unique set of narrow parallel grooves, Phobos, averaging 150 meters wide and 25 meters deep. The grooves run from Stickney, the largest crater, to an oddly featureless region on the opposite side of the satellite. One theory suggests that the grooves are deep fractures caused by the impact that formed Stickney. So something interesting about these two moons of Mars is their names. What can you tell me about their names? So what can you tell me about the names? So the two moons were named after the mythical attendants of the god of war. Phobos was the god of fear and Deimos was the god of dread. And they are, if I'm not mistaken, from Roman mythology. Because I think if comparing Roman mythology with Greek mythology, in Greek mythology it is Zeus, and in Roman mythology it is Mars, but both are the same thing if I'm correct. So yes, there are a naming convention to it. So you would see most of the planetary bodies are named after Roman mythology and Greek mythology. Deimos not only has no grooves, but it also looks smoother because of a thicker layer of dust on its surface. The material partially fills craters and covers minor surface irregularities. It seems likely that Deimos experienced many collisions in its past, so its fractures may be hidden below the debris. Ah, yes, that's why I made a mistake. You are correct. So Mars is equivalent to the Greek Ares. Same goes for Jupiter and Zeus, Neptune and Poseidon. Ah, thank you so much. That's where it came in. So I know there was something to it. So debris on the surfaces of the moons raise an interesting question. How can the weak gravity of small bodies hold any fragments from meteorite impacts? The escape velocity on Phobos is only about 11 meters per second. An athletic astronaut who can jump 2 meters high on Earth could jump 3.4 kilometers on Phobos. Most of the fragments from the impact should escape, but the slowest particles could fall back to the weak gravity and accumulate on the surface. That cushioning the layer in turn could help trap more debris. Because Deimos is smaller than Phobos, its escape velocity is smaller, so it seems surprising that it has more debris on its surface. This may be related to Phobos' orbit close to Mars. The Martian gravity is almost strong enough to pull loose material off Phobos' surface, so Phobos may be able to retain less of its cratering impact debris. So, comment. So Pluto is Hades, even though it is not considered one of the planets anymore. So that, ladies and gentlemen, was the lecture on the terrestrial planets. Do you guys have any questions? So I have only read the first Percy Jackson book. Why are you not a fan? So it's safe to say that Earth is at a kind of equilibrium as compared to other terrestrial planets. Yes, you can make that assumption. Do they have any specific way of naming the moons and planets, as in characters or just are? So there are conventions. So in general, moons and planets are named after Greek and Roman mythology, except Neptune, but we will discuss that in that chapter. Have I played Theogenesis? No, I haven't played it. So off topic. At what time would we be leaving campus? So I will let you guys know about those details. I think someone has raised their hand or not. So unfortunately, I'm not available on campus tomorrow. I have my own research to work on, but we can set up a later date and time this week that can be on campus again, if you need me on campus. So yes, Mr. Melville, you are giving away one of my favorite slides on about Uranus, but we will discuss that as well. So if you guys have no further questions, you are more than welcome to log off. I will remain active for another few minutes. So in tomorrow night's lecture, we will be discussing the 4 Jovian worlds, so Jupiter, Saturn, Uranus, and Neptune. So if you have no further questions, then you are more than welcome to log off, and I will see you all tomorrow evening. I will remain active for another minute or two. So a question. Would a semester test be in a similar format to the quizzes, except with more difficult questions and different type of questions? So yes, so it will be it's the same form as the quizzes, with 90% multiple choice questions and a few longer questions. And you will write that on ClickUp. It's a pleasure. So Jupiter's moons are named after his lovers. So that is also another slide I'm going to show you guys. So how did they detect if Google was used? So we have software that can detect it through ClickUp. So it's up to the lecturer if they want to use it or not. And in my case, I'm going to use it. So if you guys have no further questions, then I'm also going to log off. So have a wonderful evening, guys, and I will see you all tomorrow.